Right, so this sort of links to what we were talking about last term now. So last term we were sort of talking particularly about we defined a theory where we were particularly interested in the one loop amplitude. And we were saying that in string theory what we have is, whereas we were just talking about quantum field theory where you have Poincare symmetry, this fact that in string theory you define the fields on the world sheet leads to additional symmetries or different symmetries. And in particular, you have conformal symmetry. Conformal symmetry, which leads to conformal field theory. And we were essentially talking about string theory in terms of it being a conformal field theory with a particular set of fields. And we were talking about heterotic strings. Where we had, in order to maintain conformal symmetry, we had a particular number of fields. And the fields we had were some space-time bosons, which were defined in terms of complex coordinates. So this is when you map the world sheet into the complex plane, and then you define all coordinates in terms of z and z bar, which makes all the fields holomorphic or anti-holomorphic fields. Then we had, so we noticed that this space-time boson we can write as a function of z and z bar, and you can separate it into x of z plus x of z bar. But we introduced space-time spinor fields, but only on the holomorphic side, so as a function of z. And this was done because it still allows us to define space-time fermions, which you need for a theory that describes physics. But there's no need. You can introduce them and have world sheet. So you can. I think we said about that this allows us to have world sheet supersymmetry in terms of the z coordinate on the holomorphic side, but we don't have any on the anti-holomorphic side. We don't have any world sheet supersymmetry. We only have a c equals 16. So the anti-holomorphic side, we have a c equals 16 Virasoro algebra, a lot like in the bosonic string, where instead of having a 26-dimensional theory, because on the holomorphic side you've got this spinor fields. The anti-holomorphic side requires that. So the holomorphic side requires that the number of space-time indices is 10. So you've got 10 fields, bosonic fields, x mu of z bar on the anti-holomorphic side, but then you've got this additional c equals 16 part of the conformal field theory, which can be written in terms of either 16 bosonic fields, so you could maybe write like this, with I 1 to 16, and you notice this I is not a space-time index. So these fields don't map the world sheet into space-time. They live only on the world sheet itself. They're internal coordinates. Okay, so you can either write it in terms of 16 bosonic coordinates, or you can write it in terms of 32 real fermionic coordinates. So each one of the bosonic fields contributes C equals 1 to the conformal field theory, whereas these real fermions contribute C equals 1/2. And we can also say that you could complexify these fermions and write them as 16 complex fermions. If we want. So I think that's what we'll generally work with the complex fermions. So in particular, you can complexify all complex fermions, or 16 complex fermions, psi, or the capital Phi of B equals 1 to 16, such that, for example, the first one is complexified in terms of the first two real fermions. So these are, I'll just put that in as a note, what I said before. So these are internal fields. And we will see that these relate to, these end up generating the gauge sector of the heterotic string. So what we were interested in is studying these fields in terms of their conformal field theory properties, essentially, on the one loop amplitude. So although there's the tree level amplitude, turns out that's trivial, it doesn't tell you anything interesting. And then if you study two loops or higher, you also don't really learn anything interesting. But the one loop amplitude is also quite simple, and it's actually like studying it's like a vacuum to vacuum amplitude. And in this sense, like it corresponds to essentially the case where all the possible particles in the theory, so all the states in the Hilbert space, just loop around the torus and return to themselves. So the theory contains all the states. So this amplitude contains all the states, but there's no, it's very simple because it's just just a vacuum to vacuum case. And this vacuum to vacuum amplitude, so all the states are going around it, and it has to be conformally invariant, and it ends up meaning that we write the amplitude in terms of a function called the partition function, which is there, which is written as Z in analogy to partition functions in statistical mechanics. And this Z we can write as factorizing into the partition function for each set of fields individually. So the partition function for x mu, the partition function for psi mu, and the partition function for these complex fermions, which maybe I'll write this as phi, capital Phi, capital Phi. Okay. And then this whole thing, so conformal symmetry on the torus ensures that this partition function has an important symmetry, the modular invariant. So the partition function is composed of what are called modular forms, or functions which are defined in terms of transforming well under modular symmetries, which is the modular symmetry group is SR2Z. modulo Z2. But this is essentially checking that this function is invariant. So if you define the torus in terms of a complex parameter tau, so each point on the torus is written in terms of some tau, which maybe is written tau1 plus I tau 2. But the torus is given this parameter tau, then the torus parameter tau, if you essentially, this is like how you glue the ends together if you took the torus apart. You have these two symmetries, and then so minus 1 over tau, that's like, I think, if you cut torus and then how you glue it together, and then tau goes to tau plus 1, it's just translations essentially around the torus. This is called S. So this is called F, and this is called T. And these are the generators. So these are the generators of SL2C. So you only, and the point about generators is that they that you can check them, and that will confirm the group whole and the invariance of the whole group. So one more thing about this this partition function. So generally, so this part of the partition function x mu for x mu is something that isn't as interesting as this part here. So this part here is in terms of fermions. So this bit we can write maybe as ZF. So this is the partition function for the fermions, and this is the partition function for the bosons. But the partition function for the bosons, well, the main thing is that for the fermions have some freedom in them because, or there's some like variation in them because any fermion, when it transforms, so when it propagates around the torus amplitude, so I move around this torus, and it also, you can imagine it moving around, and then when it goes around like a loop, like here, or it goes around a loop here, it can pick up a boundary condition because fermions, we know, like have non-trivial boundary conditions in general. So they, so we can write. Let me just put this out. So these a fermion, as it goes around one of these two loops, so here or here, the non-contractible loops, the torus, it can pick up a boundary condition which, for future reference, I'm going to write like this. So alpha of F is the boundary condition, and I put these minus signs in just for future convenience. And in this case, in particular, you can distinguish two key cases. One where alpha of F here in this boundary condition is 1, in which case this part gives you minus, which is cancelled with this minus. So this is periodic. So this would be correspond to a periodic, or this is also the word Ramon. And then alpha of F corresponds to this being 1, which gets a minus sign. So this gets an overall aperiodic boundary condition, which is also called NF, or no short. So in this partition function here, this ZF depends on boundary conditions for these fermions. Okay. So in general, you've got so therefore, in general, we can write ZF in terms of, okay, well, maybe I'll write that after I define the, right, Right. So one thing that is fundamental now to so what we've done is we're kind of at a point now where we can start writing down stuff about the free fermionic formulation. Okay, so one thing that we have now is the following important information, which is the boundary conditions of all of these fermions. So the sign U, the space-time fermion, which from now on I'm going to write, instead of writing it as 10 components, so 10 directions in space-time, we can move and I mean, really, I'd have to sort of justify this a little bit more, but you can use the Dirac equation and show that in the light cone gauge, you can essentially rewrite the whole theory in the light cone gauge, which, yeah, I'm not going to write down the details on. Okay, so we have now to define all of these boundary conditions, which relate to the space-time fermions, but also the complex, the 16 complex fermions. Okay. And our theory essentially will correspond to a set of choices of these boundary conditions that will allow us to define this fermionic partition function in a way that the whole thing is going to be modular invariant. So these boundary conditions choices can be kind of compactly written in terms of you can write down basis vectors of these boundary conditions. So basis vectors or basis sets, and then you can think of having, for example, you might create a vector v1 where all of your boundary conditions are 1. Okay, which so now there's 8 degrees of freedom here because we went to the light cone gauge, and then there's 16 degrees of freedom on the anti-holomorphic side of the gauge or internal coordinates. So this is an example. So e.g., so this is the sector where they're all periodic. So this is saying they're all Ramond. So this is like the Ramond sector of the theory. So it's like saying, that you set all of your fermions to be periodic. And then you could also try and create other basis vectors. So you might say that all of these are aperiodic. So you could write 1 to the 8, 0 to the 8, 0 to the 16. And that would just be where you just set the space-time fermions to periodic. And then through defining different basis vectors, so whatever you choose, you then create, so these basis vectors create a sort of vector space or an additive group in terms of, if you think of it in terms of the sets. But so we usually write this additive group just for the notation. We usually write it with this symbol as equal to the span of the basis vectors. and then all the elements of this vector space become all the sectors of the theory. And each sector in the theory will correspond to some element in the Hilbert space. So all of the states of the theory. So each element, so usually we write an element of the vector space here as a linear combination of alpha. So this will be some linear combination Ni Vi is called a sector. Sometimes the word sector is often abused by the free fermionic literature, and maybe even more broadly in string theory. But I'm just going to call a sector any linear combination of basis vectors. It might turn out that doesn't really correspond to a state, a physical state in the theory at the end of the day. But that's just my definition of it. Okay. So yeah, any element of any linear combination of these basis vectors will be called a sector, and it will correspond to a possible state in the Hilbert space. And I'll just define that now, what I mean by that. Any questions or comments? Okay, so in what sense does a sector correspond to a state? So for example, let's take V1. So V1 is just one of the basis vectors, which is 1, 8, 1, 16. So this, by the way, just for some notation, this is often written as just being called the basis vector 1. Okay, just for some simplicity. So this is where, yeah, the Ramond sector on both sides. And it's also written, we usually make the conventional choice of any Ramond fermion, we just write as in, so we just write it like this. So if a fermion is Ramond, we write it, if it's an S, aperiodic, we just don't write it. So that's like just a convention, which is, yeah, you just get used to. So for example, this here, this is equal to sine u, because the gauge degrees of freedom are aperiodic, so we don't write them. But you have to remember they're there. That's just notation. I mean, people used to write it like this, which I actually quite like, but this does kind of, it becomes harder when you have more complicated boundary conditions, because you need to remember the order and what all the fermions, how they're written and stuff. So, but this, at least, once you get used to that convention, it's quite useful because you see the fermions. But yeah.
So do you write them all explicitly? So in this case, all of them are ones and all of them are ones. But if it's like 4 ones and 4 zeros, and then 8 ones and 8 zeros, which ones do you write in that?
You just write the ones that are 1. So if only 8 of these,
okay. So you separate that. Okay.
Yeah, if only 8 of these were 1 and the other 8 were 0, you write that.
Okay.
Okay. Right. So the point is that the boundary conditions in terms of state in the Hilbert space, we talked about last term about how a periodic fermion, if you think back, it was essentially because if you mode expand, if you do an expansion of the spinor fields, you have the possibility of having a zero mode which doesn't commute, and it creates a sort of Clifford algebra at 0th order, and all of the integer modes in the expansion spinor field are the Ramon modes, the periodic modes, whereas the NS corresponds to the half integer modes in the expansion spinor fields, and therefore they don't contain this zero mode, which is where you get something which has a non-trivial commutation, which means you have to factor it into the definition of the vacuum. So in the aperiodic case, we just have a kind of normal vacuum called the NS vacuum. Whereas in the Ramon case, because you have like a Clifford algebra, the vacuum is itself a state with an inherent kind of spin or helicity. So this is the Ramon vacuum. And you can actually create the Ramon vacuum by operating on the NS vacuum, but doesn't really matter for us now. So I just mentioned this because this is going to allow us to associate a sector with a state. So for example, here, what we've got here is this vector here corresponds to saying that all of these fermions are, so they're all periodic, which means they all have this Ramon vacuum. So this is like saying you've got an 8-fold Ramon vacuum for the psi mu, product with a 16-fold Ramon vacuum for the gauge degrees of freedom. So and then we could do another example. So if we take, for example, this vector here, whereas so V2 we define as 1, 8, which I'll now write in this notation, so sine mu. And I'm just writing sine mu and not writing 1 to 8 each time. It's always this 8 component. So sine mu and phi 1 to 16. Oh, so these were periodic. So these were aperiodic. Yeah, so these are aperiodic. So I don't need to write them. So this is how I write V2, and this corresponds to having, so these sine mu are periodic again, so they have a Ramon vacuum, 8-fold, and then the gauge degrees of freedom are NS. Okay, so I'll just write it like that, and then this is 16-fold like that. This would actually be a bit like saying we've got an R and then an NS. So this is R, NS. This is RR. So usually you think about, the most basic string theories in 10 dimensions as having, like a Ramon, Ramon, then Neber-Schwarz, Ramon, Neber-Schwarz sectors. And this is how you would kind of associate it in the free fermionic manner. Okay. Right. Now, let me just see the time. I was thinking to go till 12. That's right. Okay, so we've kind of said something about the basis vectors, and I wanted to come back to the this partition function. Okay, so we said that the fermionic part of the partition function is going to obviously depend on these boundary conditions. So in general, because we're considering the torus, you can either go, each fermion has to be defined on both of these non-contractible loops. So there's two BCs to define. Okay. So for each fermion, you need to say, okay, so it might be periodic here and aperiodic here. And so you actually, in order to, so a useful object is a definition which is alpha beta. And this essentially takes these sectors, because the actual basis vectors are only telling you a boundary condition in one direction. But then to think about the amplitude, and therefore to think about the partition function. So I want to get to defining this in a second. So to define a partition function, you actually need to define this boundary condition in both of the non-contractible loops. So that can be defined in relation to the basis vectors, in the sense that the basis vectors that span this vector space, all of the elements of that vector space are valid choices for the boundary condition in each loop, for each loop. So these alpha betas are just different, all of the choices for the elements in the Hilbert space. So I'll in a minute, I'm going to define the partition function, and you'll see in this definition that we will have like a product over alpha beta in the Hilbert space, so in the vector space. Okay, so but this object here, where you just write all these choices, where you have like two sectors, these are called spin structures. And they're the sort of fundamental variables in the partition function that we'll define now. So the full partition function for the fermions, so this is the psi mu and these complex fermions that are internal to the theory that I said relate to the gauge sector. Then the partition function can be written as a product of the partition function for each of those fermions. Okay, so so what this means is that each of these is a vector, right, with all of the boundary conditions in for all the fermions. And so this will be made up of things like Z11. Let's say for like for the one basis vector we defined before, so 1, where they're all periodic, so psi mu. 5 on 16. So for example, with this vector, if you put that vector as alpha and beta, so Z11 is equal to the partition function for sort of Z of psi mu, which is going to be 1, 1, because we've got periodic in both directions, because we're just saying 1 is alpha and beta. And then we multiply that by the partition function for the gauge coordinates, which is also 1, 1. This was just taking this Ramond case. And then, so what we're doing is just writing this for all the sectors in the theory, so all the elements in the Hilbert space, or the total base. Right, and there is one extra detail, which is that this formula written isn't complete. You have to add in, and I did mention these before Christmas, you have to add in an extra right, I'll use square brackets. An extra term. Let's write this again. So there's an extra term which is called C alpha beta. which are typically just 1 or -1. So typically they're just 1 or -1. Sometimes can be plus or minus I in the kind of models that we look at. But these are called, so these phases are needed. Essentially, they weight the transformations, the modular transformations in the partition function, and they're associated to generalized, what's called generalized GSO projections. So yeah, you see GSO projections in all parts of string theory, but here these are associated to a more generalized version of them, where you're essentially allowed to operate on introduce sort of operations on the fermion number within the theory for different parts of the fermions. But it doesn't really matter. But we'll come to that later. But so these are usually called GGSO phases. And so yeah, they're usually just plus or minus 1. So I'll just put they weight. You think of them as sort of weighting spin structures. And we know this whole thing here must be modular invariant. And we can also now define what are these partition functions. Okay, so fermion partition function. So so if we take a holomorphic fermion that is either Ramond or Neveu-Schwarz. So in general, we could have more complex boundary conditions, but we'll just say a holomorphic Ramond or Neveu-Schwarz, which is the same as saying it has real boundary conditions. So holomorphic RNS complex fermion is associated to a theta function. So theta function alpha of, so let's call this psi, so beta of psi. So for example, here, this function would just be a theta function, and this function would just be a theta function, but on the anti-holomorphic side. So this bit here would be like a theta function, sorry, theta to the 8, and this would be 1, 1. And then on the other side, you've got 16 theta bars, which are 1, 1. So in general, for RNS, these are equal to either theta 0, 0, theta 1, 0, or theta 0, 1, theta 1, 1. So there's only 4 choices relating to the different combinations of boundary conditions in the 2 directions of the torus. And you build your partition function from those. Okay. So all of this part here, this is just the product of lots of theta functions. And the theta function is just a modular, it's a sort of modular form with particular nice properties under the modular transformations. Which we'll come back to. Okay, so then you can just write, so essentially the form of your fermionic partition function is a product of loads of theta functions with these 4 different, which can be these 4 different options, and then in front of them we'll have to have, when we choose the different sectors, alpha and beta, we have to have this plus or minus 1 coefficient. So modular invariance restricts all of VI, so the basis vectors, and the alpha beta. In order to make such that ZF is modular invariant. Okay. Because if you remember, there's always the bosonic coordinates, so x mu. But as I said before, like the partition function for those doesn't depend on boundary conditions. So that's fixed, and it is actually independently modular invariant. So the fermionic part has to be modular invariant itself in order for the full partition function to be modular invariant. Okay. So there's a restriction on these C alpha betas and the form of your basis vectors. So, for example, if you chose maybe you could choose a vector like this, maybe, where you can put in, let's say, 1 fermion on the one of these gauge fermions. If this was a basis vector where you just have 1 complex fermion, it turns out that can't be modular invariant. You can't create a basis with such a basis vector that would eventually give rise to this thing being modular invariant. You have to group the fermions in certain ways with the boundary conditions in order for the whole thing to be modular invariant. Okay, and so these give rise, so these rules or these restrictions on the basis vectors and the GSO phases are called or we will call them the ABK rules. And we have 15 minutes, and I can just write them. And these are basically just derived by looking at the partition function, doing the S and T transformations, which define the modular group, and then seeing like how you can ensure this it's invariant. And so these are the rules that we'll just use. So I'll define them, and then we'll start. Next week we can start building models with them. So we'll see how they are used and how they work. So the ABK rules. So for the basis vectors, they are defined in terms of the dot products of basis vectors between each other. So I'll define the dot product in a second. But if you take a basis vector and dot product it with another basis vector, then we actually have to put an extra number here, which I'll explain in a second. So if we take the dot product, they have to end up being modulo 8 invariant. And I'll define this when I've written the other rules. And then you can also take the dot product of the vector with itself. So this is I not equal to j. And you have to define a number here. So this is naught mod 4. And then that's essentially there's another rule, but it doesn't you don't really need to worry about it most of the time, because the types of basis vectors that people use or always obey this rule, and it's not really worth writing out, but there is another rule here that's more of a technicality than very useful. So these are the two rules. There's only two rules for the basis vectors you really need to worry about. Okay, those two. So I'll define these two. So n I j is equal to the lowest what is it, common multiple, lowest common multiple or lowest common, get confused by the terminology. So it's the smallest positive integer, no, it's the least common multiple of ni and nj, and ni is is the smallest integer such that ni multiplied by vi is equal to 0. Okay, so usually ni would be 2. Okay, so usually, so I'll just write it here. So if we're only considering real boundary conditions, so R and NS, and we're not considering anything more complicated. If R and S only, so real boundary conditions, then Ni is always 2, and so would Nj. So Nij would be 2, and Ni would be 2. It's only when you have complex boundary conditions that these start being maybe 4. Sometimes if you have complex boundary conditions, this becomes 4. That's all. So the point is that if it's if you only have Ramond and NS, that if you multiply any vector by 2, if you multiply a vector by 2, then all of the Ramonds, so all the Ramond is 1. You multiply them by 2, it becomes 2, which is back to NS, because it's like you transport something, you get a minus sign, then you transport it again, the minus sign's cancelled, right? So you got 2 minus signs. So it's just the facts, it's like double periodicity of the fermions. And so this is encapsulated, this is mod 2, 0 mod 2. It's just saying that you get minus sign, something. Okay, and then we've got rules on the GSO phases from modular invariance. So GSO rule. So in general, if you take C alpha, so if you take the GSO phase of some sector, actually, so I'll define these in terms of the basis vectors. So easier. So So in terms of the basis vectors, if you define the GSO phase between the same basis vector, this is equal to, see if I remember this, E I over 4 VI dot product with itself. So I still need to define the dot product, which I will do in a second. And then this is equal to VI with the Ramond vector. So I'll just put in brackets here. In general, we always put the Ramond vector in the basis. So this one vector, we always put it in Well, I'll put it in the basis. So. Always. So it's usually said that you have to always put that vector in. It makes sense that you have to put it in a way because it's essentially like saying that it ensures that your theory has like a Ramond sector, which makes the whole thing, it should make it always modular invariant because you have an S sector, which gives you all of the important states and gravitational states and stuff. And then you should always need a Ramond sector, but I think I'm pretty sure that you don't really have to put this in. It could be a linear combination, but by convention, it's always in the vector space. So you may as well put it in the basis, and then you define the rules in terms of that, which means that one is a basis vector, and then any other basis vector. You can define its GSO phase in terms of itself in relation to its GSO phase in terms of 1 with this phase. Let me just double check I got the phase right. There might be a minus in the exponential. Nope, that's correct. Yeah. And yeah, there's the nice one. So then it's CVI-VJ. So the GSO phase between two basis vectors, different ones, is related to its opposite. You flip the two with this phase, this exponential. So CVJ CVI. So this is when j not equal I. What else? So you can also define a relationship between the GSO phases of like one basis vector in terms of the sum of two basis vectors. And this requires another definition, which I'll define in a second. So this requires this delta symbol to be defined, which is just going to be 1 or -1, depending on the. Basically, it'll just depend on the boundary condition of the space-time fermion sign mu. But then this is just the product of the two GSO phases. Okay. So this thing here is like equal to 1 or -1 if so I write it like this: dI of sine mu is Ramond. So if it's 1, then it's NF, but 0, and then if it's Ramond, it's -1. So if the space-time fermion is Ramond order, so it's like the spin. It's called the spin statistics operator because it relates to the to the sine mu, so the space-time fermion. Right. So this is a K. Yeah. So this relates the GSOs of a sum on the bottom to a product. Right. Well, yeah. Okay. And then see, we're nearly at 12 now. Yeah. I think we'll probably stop there. Could write that down, but I think we'll come to that. Okay. I think that's a good place to stop. These are all of the GSO rules. There's one thing I haven't defined, which is this dot product. So the dot product. So the dot product is I can write it in a very simple way because everything's a complex fermion. All of the things with at the moment we've only talked about sine mu and the 5R. which are all complex. If you had real fermions, you'd have factors of a half in this dot product. But because we've only got the sign mu, which is complex, and the phi bar 1 to 16, the dot product's quite simple. It's like a Lorentzian dot product in the sense that it's got a minus sign to the anti-holomorphic side. So there's so vi dot vj for what we've defined so far would simply be the sum. So it would actually just be the sum of alpha of sine mu. So this is just from. So this is obviously got 8 components to it. So this would kind of be from 1 to 8. So mu equals 1 to 8. So really this is if it's periodic, then it's 8, and if it's aperiodic, it's 0. Okay. Minus. So then, like I said, it's sort of like a Lorentzian in the sense that it's got a minus sign for the anti-holomorphic side. So it's got a minus and then a sum over b. I think I used b before. So b 1 to 16 of the boundary condition for these gauge degrees of freedom. Okay. So for example, in the 1, so I'll do an example just with this 1 vector. So 1 dot with 1 is equal to 8 minus 16. Because it's all these boundary conditions are 1, so you just 8 minus 16. Okay, so that's all of the ABK rules. I think I defined everything. Yeah. And then next week we can start using them to build models. But so the point is that now with these rules, as long as you follow these rules, you can define a basis, and you can use those basis vectors will allow you to choose only certain GSO phrases. And then what you have is you can then write the partition function down as long as you follow these rules, and it will be modular invariant, which means it's a valid string theory model. And you can get the Hilbert space, you can get all the states, and you've got a valid theory which obeys all the symmetries of conformal field theory on and diffeomorphism invariance and whatever. So okay, I think that's enough. I'll stop the thing.